Okay, so the final talk is by myself, which is catalyst-controlled CH functionalization. And it's a really tough act following two really spectacular talks. So congratulations to the first two speakers. And so, you know, I've been very fortunate to be involved with so many collaborators within the center and also beyond the center as well. And indeed, our program's been enriched with so many, you know, good suggestions from everyone within the center, as well as many active collaborations. So I feel very bad today because I've only got 20 minutes to talk, so I can only describe collaborations involving a few. And so we're going to talk about developing new catalysts for site-selective intermolecular CH functionalization. And so in this program, we're indebted to lots of insights from computational chemists. So Jamal Muzayev has collaborated extensively with us, and now Ken Hauk is adding an extra new dimension to what we can do in this area. Also, we'll describe some applications of this chemistry. One will be towards an initial program on total synthesis, but that's been inspired by some ideas and collaborations with Brian Stoltz. And then we've also been challenged by our industrial collaborators to think about using the chemistry towards more pharmaceutically relevant projects. And I'll just illustrate how that is going, some collaborations with AbbVie as well as Novartis. So the grand challenge for the center in general is this concept of how do you have reagents that are active enough to react with CH bonds and yet be able to distinguish between these gray CH bonds of very similar reactivity. And so our approach is to focus on catalyst-controlled CH functionalization. More traditionally, and these have developed extremely well, is the idea of doing intramolecular CH functionalization or having substrates that have inherent reactive sites. And it could be a tertiary CH bond for radical chemistry, or it could be certain heterocycles will tend to functionalize at a specific CH bond. And of course, another approach that's really become incredibly powerful these days is if you've got a directing group on your substrate that will coordinate to the metal and then place the metal close to an unactivated CH bond, resulting in overall functionalization. But these approaches, even though now they're very established, do rely a lot on the substrate to really drive the chemistry in a controlled manner. And what we want to do in the center is move away from that and rely on the catalyst and its ligands. And so, for example, Jin-Kwan Yu in the center, you know, has done extensive work on having now rather weak directing groups. So the metal and the ligands can really control the site selectivity. And of course, we've already seen a wonderful talk about enantioselectivity today, where those ligands sort of dominate how the chemistry will work. Our approach is to have no directing groups and really rely on the metal to be able to do that selective CH functionalization. So the ligands and the shape of the whole complex will control which CH bond is going to be functionalized. And so the way we're doing this is actually using diazo compounds. So we have metal catalysts that will decompose diazo compounds. The driving force for this reaction is generating really stable nitrogen gas, of course. And in the process, we generate a reactive metal carbene that's reactive enough to go for a CH bond, and then allow a complete catalytic cycle to occur after inserting into that particular CH bond. Now, the challenge with this type of transformation, it's actually kinetically very straightforward. It's very fast. But typically the challenge is to be able to select which CH bond is going to be functionalized. And our control elements here come from 2 points of view, because we want to rely on intermolecular reactions. No doubt the intramolecular transformation is already very well established. And the way we're going to control the intermolecular reaction is to use an appropriate carbene source that will be sufficiently reactive but also have the capacity to be selective in this CH functionalization. and then to control that selectivity by modifying the nature of the ligands around the metal itself. And so the types of reagents that we developed were these called, what we call the donor acceptor metal carbines. And we developed these a long time ago. So in the mid-1980s, what you would find is that the traditional carbines either had 1 or 2 electron withdrawing groups. And these transient carbines have got very little back bonding from the metal, so they're naturally very electrophilic. And obviously having further electron withdrawing groups enhances that electrophilicity and reactivity, but causes challenges when we're talking about selectivity. So what we developed, a pretty obvious thing to do actually, is to replace one of the electron withdrawing groups with an electron donating group that will tame the reactivity of the carbene, but still leave it sufficiently reactive to be able to do CH functionalization, but now with the possibility of greater control. Now, the other feature of the program is the catalyst itself. So our catalysts are based on rhodium acetate, which was developed in 1973. And about 20 years later, we began exploring developing chiral catalysts based on rhodium prolinates. Started in 1983 and then published in 1996. This catalyst we called rhodium DOSP. And then very soon thereafter, we began to show that using donor acceptor carbines with rhodium DOSP, you could actually do enantioselective intermolecular CH functionalization. It was the first example of a highly enantioselective intermolecular CH functionalization with these type of carbines. And so then for many years, rhodium DOSP was the catalyst for us. We actually published 46 papers on various aspects of enantioselective intermolecular CH functionalization using this catalyst. It performed extremely well at activated CH bonds, benzylic, allylic, alpha to oxygen, alpha to nitrogen, and there was a range that we could develop with that. About a decade later, we developed another catalyst, which is a catalyst we call rhodium PTAG, and that was inspired actually by our ability to be able to do CH functionalization of adamantane, leading to the development of this catalyst. And this catalyst did a lot of different types of carbene reactions, but didn't have much impact on our CH functionalization program. The catalyst that did was a 3rd generation catalyst we developed, again inspired by the fact we could do highly enantioselective cyclopropionation reactions. So these triaryl cycloprophanes, and we found that these were much more sterically encumbered than any of our previous catalysts, leading to the possibility of controlling which CH bond based on this really large, crowded shape of these catalysts. And so after this, we began to evolve this further. And actually, when I did present at this virtual symposium in 2016, we disclosed this particular catalyst, which showed site-selective reactions at unactivated methylene groups. Now, since then, we've developed a lot of other catalysts, some of them based on the 2nd generation catalyst, further development of the 3rd generation catalyst, which give rather unique site selectivity, and that's really what I'm going to be talking about today. Okay, so in terms of these catalysts, so rhodium DOSP, when it developed, the basic structure of the dirodium tetracarboxylate was not considered to be ideal for the design of chiral catalysts because the rhodium has 2 faces and the carboxylates all point away from where the carbene would bind. And so when we did develop rhodium DOSP and found it was really effective, we made the hypothesis that maybe these catalysts adopt a higher symmetry than the ligands themselves. So we imagined that if say, the aryl sulfonyl group on the proline was a really big group that either had to point up or down, but not on the edges of the catalyst, then you could actually potentially have a complex that's actually, much higher symmetry than the catalyst itself. And so we proposed actually, if the groups were all up, it could be C4 symmetric. If it was up, down, it could be D2 symmetric. If it was 2 up and then 2 down, it'd be C2 symmetric. And indeed, we actually made the hypothesis that rhodium DOSP was actually behaving in this D2 symmetric arrangement. This leads to a very nice prediction of the attack occurring at the ray face of this catalyst when using the rhodium S-DOSP enantiomer. And even though this model itself is now being questioned by us because we're seeing that this catalyst may be more flexible than we originally thought, it actually is a driver of how we design our new catalysts. So for example, so where we're going is that rhodium DOSP itself, in all those 40 to 50 papers we published, we showed that when you're using a donor acceptor carbene, you can get pretty nice reactions at activated secondary CH bonds. So allylic, benzylic, alpha oxygen, and nitrogen, as I said earlier. But obviously, this program was all substrate control because basically we had one catalyst. So what we want to do is modify that catalyst so that now we've got the possibility of controlling the chemistry effectively by changing the size of the system. Electronically, the tertiary CH bond is preferred, but if you really sterically make the catalyst very demanding, you could push it towards secondary and even towards primary. And so the second generation catalysts, here are the two that are really the new ones that are driving it these days. These are C4 symmetric, so the tetrachloropetad adopts the C4 symmetric arrangement. It was understood that that would be the case even with the tertiary butyl derivative that was developed by other groups, and we find that tetrachloropetad has that feature. The tetraphenyl derivative is really interesting because you basically got 16 phenyl rings on the outside of this structure, and these adopt as tilted arrangements, so they actually have a sort of additional propeller type chirality that is important for their anti-selectivity. And then the third generation catalyst, these are the sterically most demanding, can adopt different shapes depending on how they're arranged. So some D2 symmetric, the one on the top right is the one that we published in that 2016 Nature paper. And then some of our new ones where we have an orthochloro functionality, they adopt the C4 symmetric arrangement. And then one with extended arrow groups actually adopts a C2 symmetric arrangement. And these catalysts look sort of overwhelming, but actually they're really easy to make. As I said, the asymmetric cyclopropionation is highly anti-selective. Then you only need to hydrolyze the ester to the acid and do a ligand exchange. And then you can get a lot of diversity by doing multifold cross-coupling on the catalyst itself. And so here are some of the key ones we've developed. So the one on the right would involve a 12-fold Suzuki coupling, for example. And then, as I mentioned, the fact we can do CH functionalization of adamantane led us to this tetrachloropetad derivative and in a very short synthesis as well. So when I talked last time, I showed you how this meta-disubstituted aryl catalyst was capable of doing a really clean reaction on the methylene group next to the methyl. So it could distinguish sterically between all the other methylene sites. So here's a reaction with octane. Here's a reaction with alkyl halides. Again, it's always going at the C2 position. And these reactions go with good site selectivity, diastereoselectivity, selectivity, and these are a very effective chiral catalyst as well, giving high in antiselectivity. You could also have silyl functionality presence, even ester functionality. Again, you'd go for the most sterically accessible methylene site. So basically, when I talked last time, this was the stage we were at. We had this particular catalyst, and where we've moved now is we've actually brought in some new catalysts. One, the tetrachloropetad is actually less sterically encumbered, so it will go cleanly for tertiary CH bonds. And then this, as I said, 12-fold Suzuki coupled catalyst actually is really sterically demanding, and so would drive the chemistry towards the primary CH bond. And I'm just going to illustrate with a couple of examples what we can achieve with this. So this is illustrating the tertiary selective catalyst. And you can see various simple alkanes will work. Again, you can have functional group compatibility in this reaction. And then you can broaden the type of aryl groups to change the aryl functionality, and including bringing in some heterocycles to work with this chemistry. Now, these are relatively small substrates. You can actually do the chemistry on more elaborate substrates. And again, this catalyst would go for a tertiary CH bond, but it will go for the sterically most accessible. So in this reaction with vitamin E, you've got a lot of benzylic sites, which are electronically favored, as well as 3 tertiary sites. But the reaction goes really cleanly for the most accessible tertiary site. And again, the reaction, depending on which enantiomer of the catalyst you're using, you can control which diastereomer is produced. And you can even improve that selectivity if you do the reaction at lower temperature. But at that case, you begin to lose a little bit. Now here, again, we've done many examples on the tertiary, on the catalyst that's now primary selective. I just want to illustrate a couple of substrates just to show you how this works. So these substrates are relatively small, but obviously they've got primary, secondary, and tertiary CH bonds. And also groups like a silyl group, a siloxy group, would tend to activate the adjacent methylene. However, this is a very demanding catalyst, and it actually will only go for the primary CH bond. And in these substrates, there are actually 2 sets of primary, but the catalyst will go exclusively for the most accessible methyl. And this is a really very effective catalyst in terms of asymmetric induction. And so you get extremely high diastereomer selectivity in this reaction. And just to emphasize that this is really under catalyst control, if you use the other enantiomer of the catalyst, then you get totally into the other diastereomer. And again, if you think this molecule is too small, you can also do this chemistry on steroids. So here's the steroid, obviously many, many CH bonds. We're just highlighting a few of them. We've got multiple tertiary CH bonds that are marked here. Some of them are allylic, which should be really reactive. But it turns out the catalyst will only go, the tertiary selective catalyst will only go for the blue CH bond, which is the sterically most accessible, and it'll go quite effectively for that position. And then the catalyst on the bottom is the primary selective catalyst, which again, there are many primary CH bonds in this structure, but it'll only go for the red CH bond, the most sterically accessible. We've also been able to push this further towards selective functionalization of secondary CH bonds. In other words, when you have several secondary CH bonds. And so here's an example where you're actually getting the chemistry to go at a methylene next to a methyl over a methylene that's electronically activated next to a benzene ring. And the catalyst that works well with this is this orthochlorocatalyst. I'll explain a little bit more about this in a second. Which adopts a C4 symmetric structure. And then another system we've been looking at is desymmetrization of cyclohexanes. So if you have an alkyl group on a cyclohexane, that makes it pretty challenging for CH functionalization because you have several relatively similar CH bonds. But we've got a catalyst that will go cleanly for the C3 position, will not hit C5 or C4. And so basically you will desymmetrize the catalyst. And this is that 16-phenyl catalyst that we have developed. So let me illustrate this work a little bit further. So the C4 symmetric catalysts are really interesting. We made a whole family of these by now. And basically, the interesting feature, if you have an orthochloro functionality, then these catalysts always adopt this C4 symmetric arrangement. And another interesting feature of this, if you look at the green color, which is where the chlorines are, you can see they're always to the left of the arrow ring. In other words, you have an induced new stereogenic center, basically axial stereogenic center generated in these complexes. So the chirality of the cyclopropane induces the chirality of the axial chirality in the complex. And these catalysts, the one that's best in terms of enantioselectivity is the 5-bromo derivative. That sort of breaks the C4, not breaks the C4 symmetry, but results in differentiation between the 2 sides when the carbene binds to that rhodium. And so with that catalyst, just to illustrate what you can do in this benzylic versus the terminal C2, a standard catalyst like rhodium tetrachlorometad, not surprisingly, does a really good reaction to the benzylic site. But when you use this new class of catalysts, you can see all the blue, that's the amount of the material that's going with attack at the terminal C2. And indeed, we've been able to show that this works with a variety of substrates. So this just illustrates some of the scope of the chemistry with different groupings. Again, you can have heterocycles as part of the substrate or as part of the carbene, showing you the breadth of possibilities with this type of chemistry. And indeed, this is actually where Brian Stoltz joined us, because, you know, at the moment, this looks like an exotic CH functionalization, but he saw a great opportunity where we might be able to use this in synthesis. And so now we've got a really active program trying to make these, the Cylindrocyclophane natural products. And basically, this just illustrates how we can use the chemistry to make the core of these natural products, the macrocyclic core. So basically, we've developed this palladium catalyzed cross-coupling, which is formally a CH functionalization to make the desired diazo compounds. And then the second step, this is the big one, where we are getting selective reaction to occur at that C2 methyl. And again, this is going in good yield, good site selectivity, good diastereoselectivity, selectivity, and good enantioselectivity. Then we do another palladium catalyzed cross-coupling to generate the new diazo. And now we repeat the reaction, but now we're doing it intramolecularly, hitting one CH bond. And because we're generating a new stereocenter that now has a symmetry in relationship to the original one, the resulting product is strongly enriched. So the resulting product is produced with very high enantioselectivity. The second catalyst is trying to do what's tended to be an incredibly difficult challenge for CH functionalization, which is functionalization of these alkylcyclohexanes. And really, getting a solution to this has been very challenging. These are some of the best CH functionalization processes out there. And you can see with something like an alkylcyclohexane, there's very little control, either in CH oxidation or in the last two using really bulky free radical reagents. You can see this is a reagent developed by Eric Alexanian in the middle there. It is so big, it won't do tertiary chlorination very much, but it doesn't distinguish between the methylene sites very much in the cyclohexane itself. And then another very bulky reagent using this tungsten molybdate type system. And what you're seeing here is, again, you can, with a tertiary butyl group, you can block the C2, but you get a rich mixture of C3 and C4, and also diastereomers is produced. And so we were shocked when we found that our catalyst, unlike many of our other catalysts, actually did exceptionally well in this reaction. So when we took tertiary butyl cyclohexane, got 88% yield. And the results are so good, I have to show a bit of a spectra as well, because the site selectivity against C4 is huge. The signal for C4 occurs at about 3.28 in the NMR, and it's actually missing. And then also the selectivity between C3 and C5 is really good, because you can see that what we call the C3 diastereomer is actually due to C5 functionalization. And you can see it's a strong favor at C3. And then on the left illustrates the enantioselectivity on the reaction. That's a HPLC trace, so it goes in greater than 95%. And so this is a pretty general reaction, works with all sorts of alkylcyclohexane. I'm focusing on the diastereoselectivity because that's the desymmetrization result. And not surprisingly, as the system goes bigger, from methyl up to TMS, you get a steadily improvement in the desymmetrization. And this chemistry is applicable to a range of different aryl groups, as well as, again, a variety of heterocyclicity. Now, with all of our program, through the collaboration with Jamal Musayev and Ken Hauk, we're actually getting a really good understanding of how these catalysts work. And one of the things we realized with this tetraphenyl PTAD derivative, that the phenyl groups had a really interesting feature because they tend to tilt. And in the X-ray structure, we found 12 of them tilted one way and 4 tilted the other way. But when we did computational studies on this, we found that the most stable structure was actually them all tilting one way. And so that leads to like a propeller type chirality, again, in the, sort of set up by the initial chirality of the ligand itself. Now, because it's C4, it's got two possible faces to it. Now, the face with the T-butyl groups on the back is really statically demanding. That's the structure 2B. And so what we find is when it's coming in from the front, that this is, again, preferred with all the tilts going one way. That's structure 2B. Now, one thing about this catalyst, it is fairly rigid, but it's not totally rigid. So there's some room for breathing, and I think you can see in 2D, the catalyst looks a little different in shape from the 1D before the carbene bound to it. So the blue is the phenyl ring, and the green is the trichloroethyl grouping we're using. Now, interestingly enough, when the tertiary-butylcyclohexane approaches this, again, it approaches from two sides. And the only carbon that can approach is actually the C3 position, because when it attacks at C3, the tertiary butyl group is sticking out of the cavity. But when it attacks at C4, the tertiary butyl group is actually banging into the wall of the catalyst. We can't actually make that complex because it just doesn't fit. And so this explains why we're getting such C3 selectivity with this particular catalyst. Okay, so what I've been showing you is that, you know, we've got a whole family now of catalysts. Actually, Justin Dubois coined the idea of having a toolbox of catalysts. So we're trying to build our toolbox here. And initially, our studies are focused very much on the fundamental studies. So earlier on, we looked at activated systems like benzylic positions and showed we could choose between the secondary and the tertiary side. More recently, we can do it on totally unactivated CH bonds, either going for primary, secondary, or tertiary. And then now, and more recently, we're looking at the pharmaceutical relevant substrates, or substrates for total synthesis. So the one says JAX 2018. That's the one for the CH functionalization related to the total synthesis with Brian Stoltz. I've also described the cyclohexane functionalization. But we're also looking at things like the pyridines. We're trying to get different catalysts to go for C2, C3, or C4. We're looking at cycles as well as small rings, like, for example, cyclobutanes, where, again, we'll use catalyst control to functionalize, and even these bicyclopentanes, where we go cleanly for the tertiary side. And all of these studies are pretty close to completion, so they should appear in the next few months or so. Okay, so finally, I'd like to acknowledge the group. And when I say the group, I'll start off with the center. It's been amazing having these intellectual discussions across the center. It's been a real pleasure to be involved in this. In terms of, this is a picture of my group. In terms of the key people that are involved in the work that I've talked about today, Huangbao Liao was the one who really drove the initial studies into unactivated primary, secondary, and tertiary CH bond. Wenbin, who's right in the front here, is responsible for the orthochlorocatalyst, is having a really big impact on our program. We've also got JT Huw here, who's responsible for the functionalization of the cyclohexanes. We've got Zach Wren, who's responsible for the computational support of all our programs. And then let me highlight Zach Garlitz here, because he's actually the one who's really sort of coordinating our applications, the pharmaceutical applications. Should also acknowledge Aaron Bossi, because he's the one who's leading the collaboration with the Brian Stoltz group, and that's been a lot of fun. Finally, I'd like to acknowledge the funding from the NSF and the center, as well as from AbbVie Novartis. Thank you. Okay, so I have some questions. With 2-chlorobromo catalyst, does CH insertion outcompete terminal olefin cyclopropionation? I couldn't recall if Wenbin had shown that. So So it's rather interesting because early in my career, we did all cyclopropanation, and then we seemed to do similar types of reactions with similar substrate that did a CH functionalization. And the reason for the big change is indeed the aesthetics of the catalyst. In other words, if an alkene is sterically accessible, it's really prone for cyclopropanation, but if it's at least cis disubstituted and definitely trans disubstituted, then it will be a substrate for CH functionalization. So probably the primary alkene would still be cyclopropanated, but I don't think we've really challenged it with Wendig's catalyst. She's sitting in the front and she's sort of nodding. I'm not sure what it means though. Another question, how do the last generation catalysts behave with more electrophilic carbines, say mono-acceptor? That's a great question. And actually we had high hopes because of these catalysts being so sterically demanding that we could move from donor acceptor carbines and really start to get control with acceptor carbines. Unfortunately, we've studied that, and they're not terrible, but they're nowhere near as good as we'd like. They're nowhere near as good as reaction with donor acceptor carbines. So that is a limitation with the chemistry. You need to have something that sort of modulates the overall reaction of the carbene, still maintain the electrophilicity. So you do need the acceptor group, I think, and then and have the control with the donor. But that is a challenge going forward. How much further can we broaden the scope of this chemistry? Oh, someone asked about the temperature. So 39 degrees, so that was done in refluxing dichloromethane. So that's why it's a particular temperature. We can operate under lower temperatures, but and often do, but the advantage of doing it under reflux, it makes it just easier to make sure the system is really dry and really there's no oxygen there too. Most of the chemistry we do can be done under very easy conditions. The cyclopropanation can be done in the open air, for example. But when you're doing the tough CH functionalization, then you have to have more. Okay. Well, there are no more questions. Well, at this stage, let me thank everyone that have joined us today. It's great that we've had such support for these meetings through the 13 meetings we had. And also we've had two great lectures, and the third one wasn't okay, but that's the way it goes. Remember our next lecture, next session, we're trying to get it scheduled so people know when the meetings are going to be. The program isn't fully aligned, but I think it's going to be really exciting because that definitely Francis Arnold, for example, is developing incredible enzymes for doing selective CH functionalization. And Richmond Sarpong is one of the leaders in doing total synthesis using CH functionalization. So I think it's going to be a great event. So hopefully you'll all join us then. And so please join me to thank the audience and I suppose the speakers.